which method to use? Actually, we could convert a number from any base to any base using each of the three mentioned methods. And you could try it. It actually works. It's not very comfortable in every case, but I think you could use every method every time. However, in some cases, one method might be more comfortable than another. Mostly given that you are a human being. A computer could do every one of those methods in any case, and is still going to stay happy. Some tips about which methods to use in any case. So, whenever you are converting from a small base to a larger base, I recommend to use the direct evaluation. For example, whenever you are trying to convert from base 2 to base 10, we actually did this in this lesson already. This is the case for direct evaluation. Another tip, whenever you convert from a large base to a smaller base, I recommend to use the remainder evaluation. For example, whenever you convert some number from base 10 to the binary base, to base 2. We are going to look at some examples, mostly to make sure that you know how to choose yourself which method is the best one for every case. Let's look at some kind of example, how to convert from decimal to binary. For example, how to represent the number 30,145 from base 10 to base 2. We are going to use the remainder evaluation method, and that is because 10 is larger than 2. This is how it's going to look like. We are going to have this large kind of table. First, we put the original number here. This is the number we want to convert from base 10 to base 2. And we just try to divide it by 2 every time. And we get bit by bit all the bits of the number. And we can get them using the remainders. On the right column, we see the remainders. And on the left column, we have all the quotients. As we mentioned before, you can always check that this number times 2 plus this number equals this number. There are always these kind of triangles, and you can always check it. You can always, for example, this number times 2 plus 0 equals this number. This time you can see all the result yourself. We can just check some of it to make sure that it actually works. This is the calculator in the regular mode, like usual people use it. We're just going to check, for example, this number divided by 2 to check the result. And indeed, this is the right result. And we have this .5 thingy because of the remainder. For example, if we check the divisibility of another number, 15072, and we try to divide this one by 2, we get exactly this number, because the remainder is 0 in this case. If we just keep up with the same procedure to get all these remainders, eventually we get a list of remainders, which is just the resulting number. If we start writing it from here, from below, so we just write it here, 1, 1, 1, 0, 1, and so on, which is just this number that is written here, 1, 1, 1, 0, 1, and so on. And it's a pretty easy way to get the result. Even it is pretty fast. If you can look at the numbers on the left column, each time we get a new number, it is about factor 2 smaller than the number above it. So it's not going to take so long until we get to the last number, which is 1, and find the full representation in binary. Another example, converting binary to decimal. I remind you that the last example was from decimal to binary, and this is the opposite direction. And for example, we want to represent this number 1, 0, 1, 0, and so on, which is in base 2 to base 10. And this time we are going to use the direct evaluation method, and that is because 2 is smaller than 10. And it is going to work about this way. We just evaluate the number according to the definition. So we begin from the lowest digit. At least that's how I like to do it, just to make sure that I get the calculation right. And we just multiply every digit by its way, its relative way in the number. So the way of the first digit, of the first bit, which is 1, we can see it here, is 2 to the 0. So we just calculate 1 times 2 to the 0 plus 1 times 2 to the first plus 1 times 2 to the second and so on. And we just calculate it the usual way in base 10, and we get a result in base 10. This kind of calculation is pretty easy because we know how to do this kind of calculation in base 10. At least I hope that you can. If you can't and you find it difficult for some reason, you are allowed to use a calculator to do this. Okay, it's not going to damage your understanding in any way. You could do it. Okay, another example, a bit stranger, would be to convert from decimal to ternary, which is base 3. This time we are trying to represent the number 101 from base 10 and convert it to base 3, which is also called the ternary system, or the ternary numeric system. We are going to use again the remainder evaluation method, again from the same reason, because 10 is larger than 3. I remind you that when we tried to convert from decimal to binary, we used exactly this same method. We used the remainder evaluation even in that case. Even if we had to represent this number in base 4, I would still choose this method for the conversion. Mostly the difference from the other case when we converted to base 2 is that this time we are going to divide by 3 instead of 2. And the remainders will also be calculated modulo 3 instead of modulo 2. Let's look how it looks like. We take the original number 101 in base 10 and we write it here. We write it on the first row on the left, and then as usual we just divide every time. This time we are going to divide by 3. On the right column we are going to write the remainders, and the left column is going to contain the quotients. This time it might be a bit harder because it might be a bit harder to divide by 3. If you are very tough, you could do this on your head. So we are going to divide 101 by 3, and the result is going to be 33, and the remainder is 2. And you might be asking yourself, okay, but how could I know this? So let's open a calculator. Maybe your calculator looks something like this, like the standard one. If you try to calculate 101 and divide it by 3, you are going to get something like this, which is 33.6666. If you are experienced, then you know that lots of 6 means 2 divided by 3, and you could infer that the remainder is 2. But it might not be the case, and for larger numbers, you just might not know the remainder. For example, I don't know, maybe if we just pick a strange number and try to divide it by 7, and we get this suffix, we don't know the remainder. It's not very cool. So, if you have a bit more advanced calculator, you could actually use, okay, I clicked the programmer one. You probably have it too in your computer. So you could use the mod button. Okay, you see it here. This is the mod button. I could, for example, press 101 and then click the mod button and 3, and I get the result of 2. It might be possible that you don't have this at all, and you still want to calculate the remainder. It's not a problem. You could do something like this. You write the number that you want to divide, then you divide it by 3, and you get a not very nice number, but you can still see that the basic result is 33, at least the integral part of the result. Now we could take 33 and multiply it back by 3, and we get 99. And because the difference between 99 and 101 is 2, we know that the remainder is 2. These are just some basic ways to find out the remainder. We keep up with the next number, 33. If we divide it by 3, we get exactly 11, which means that the remainder is 2. And we just keep going. Again, we still have this triangle property of having this number, for example, 3 times 3, which is 9, plus 2 equals 11. And again here, 1 times 3 is 3, plus 0 is 3. Eventually, we just get this number, 10202, on the right column, which is the result we wanted, the conversion to base 3. And we obtained this. If you want, you can check it out later. There are some exercises that you could do now. I will just say some words about them. The exercises, at least the first part, is mostly about conversion between bases, and it could be a bit tiring if you do it for a long time. However, I do recommend that if it is your first time that you ever see these kind of things and the ideas of bases, and maybe the first time you see the binary base, I really recommend to do all of them in the order that they are presented. Even if it is a bit tiring or dull, but please make the effort to do this. Another thing, there are some mostly interesting questions when you move on. After you finish with the really basic stuff, you get to some more advanced questions. Don't be scared. You don't have to do all of them. In fact, every exercise that has the bonus mark next to it is not required for you to understand the next lesson. It will make you smart probably, but it is not required. If you are finished with the really mandatory stuff, you could move on, but if you want to research and think about it more, just to make sure you understand everything, then you could afford to do all the bonus exercises. Truly, they are not that hard and they will probably really benefit you. See you next time.